You work hard to keep ordinary things from spinning out of control. Bills, deadlines, conversations that didn't go the way you hoped. And then a night like this arrives, when the house finally goes quiet and you can sit down or lie back and let the weight slide off your shoulders for a while. In this room, everything looks still. The lamp, the door, the phone in your hand, your own chest rising and falling at a slow, steady pace. To you, nothing about this moment feels extreme, but every second of your life has been shaped by emotion you have never felt. Right now, as you listen, the ground beneath you is turning at about 1,000 miles an hour. The planet carrying you is racing around the sun at nearly 67,000 miles an hour. The sun itself is circling the center of the Milky Way at close to 500,000 miles an hour. And our entire galaxy is gliding through space, crossing the faint afterglow of the Big Bang. If you added all of that together, your body would seem to be moving through the universe at unthinkable speeds. Yet your drink doesn't tremble. The walls don't blur. Your stomach doesn't drop the way it would on a roller coaster. To you, it feels like nothing is happening at all. That quiet is not an accident. It is part of how the universe works. Far away, there are places where motion is impossible to ignore. There are stars so dense, they spin hundreds of times a second. There are regions around black holes where space and time are dragged around like water spiraling toward a drain. On the smallest scales, every electron in your body carries a kind of built-in rotation that never turns off, a microscopic momentum written into matter itself. From the title, you already know the big question tonight. Why is everything in the universe spinning? But there is another question, just as important for you, sitting here at the end of a long day. If all of this motion is real, why do you feel so calm? You clicked on this because part of you enjoys hearing the universe explained in plain, honest language. And you also came here for something you rarely get during the day. A chance to relax without completely switching your mind off. To learn something deep and quietly impressive without having to fight through equations or sit up straight at a desk. Tonight, at a gentle pace, you are going to follow one thread that runs through almost everything. Spin. You will see how tiny ripples in the newborn universe may have set the first motions in place. How clouds of gas collapsing under gravity began to rotate, passing their momentum down to stars, planets, and eventually to the world under your feet. You will see how the turning of Earth gives you day and night, weather and tides, and a magnetic shield that silently protects you from a storm of particles the sun throws out every second. You will drift out to the extreme places, where rotation becomes so intense that it bends the flow of time and changes what words like fast and slow even mean. You will zoom back down into the interior of atoms, where spin helps define the very rules that matter must obey. You will look at galaxies that should tear themselves apart, but do not, because something unseen is holding their spin together. And you will trace a line from the way light is polarized in space to the way the molecules of life on Earth chose left instead of right, giving your DNA its familiar spiral. By the time you reach the end, you will understand something most people never pause to think about. If this constant turning ever stopped, even for a moment, the world you know would fall apart almost instantly. The air, the oceans, the climate, the orbit of Earth, the structure of the galaxy, the chemistry inside your cells. Everything depends on motion that feels to you like perfect stillness. That is the quiet promise of this night. Along the way, nothing will be rushed. You are not here to keep up with breaking news or memorize numbers. You are here to let the big picture settle in, one clear idea at a time, while the smaller noise of the day fades into the background. You do not have to solve these mysteries. You only have to listen as they unfold. As you breathe in, you can imagine the planet you are on turning gently under a sky you cannot see from here. As you breathe out, you can let go of one more piece of the day, knowing that the forces holding you up right now have been at work for billions of years. The stillness you feel is not the absence of motion. It is the harmony of motion. Tonight, you will follow that harmony back to its source and watch how it shapes your sense of time, your idea of balance, and even the way you move through your own life. You will see that you have never truly been standing still, and that this is not a reason to worry, but a reason to feel oddly reassured. The universe has been carrying you all this time without demanding that you notice. So settle in. Let your shoulders drop. Let your jaw unclench. You are riding on a spinning world, inside a spinning system, inside a spinning galaxy. And somehow, you have been given a quiet pocket of time to learn why. Take one more breath, and when you are ready, we will start with the simplest question of all. If everything is turning, why can't you feel it? You've probably had this experience before. You're sitting on a plane, maybe heading home from a long trip or visiting family. The engines roar during takeoff. The wheels lift from the runway, and for a moment, your whole body feels the acceleration. Your back presses into the seat. Your stomach tightens. You know you're moving because everything inside you says so. But then, 10 minutes later, the plane levels out. The seatbelt sign turns off. The noise becomes a steady hum. You take out a book or open a drink, and suddenly it feels like you're barely moving at all. You can pour water into a cup without spilling it. You can fold a napkin, tap through your messages, or stare out the window, feeling strangely calm. If someone didn't tell you the plane was cruising at 500 or 600 miles an hour, you would have no way to know. Your body doesn't measure speed. It only measures change, acceleration, turbulence, sudden dips, the push and pull of forces acting on you. That's what your senses react to. When motion becomes smooth and steady, your inner alarms turn off, and the experience becomes almost indistinguishable from sitting still in a quiet room. That same principle is working on you right now. Earth is spinning at about 1,000 miles an hour where you're sitting, but everything around you, the chair, the carpet, the walls, the trees outside, the air itself, is spinning with you. There's no sudden push, no tilt, no shifting wind, nothing for your senses to grab onto. The motion is so consistent, so even, that it disappears from your awareness. This is where one of the simplest and most powerful ideas in physics steps into your life without you realizing it. You don't need to know the math behind it. You have lived it every day. It's the idea that an object in motion will stay in motion unless something forces it to change. You could call it persistence, or steadiness, or just the universe's way of conserving energy. But whatever name you give it, It explains why the spinning of Earth is something you don't feel, even though it has shaped every hour you've ever lived. If you were suddenly brought to a stop, you would feel it instantly. If Earth suddenly slowed by even a tiny fraction, you would sense the shift the way you sense a plane beginning its descent. But because nothing in your everyday environment forces a change in your motion, your senses register calm instead of velocity. Astronauts describe something similar aboard the International Space Station. The station circles Earth at about 17,500 miles an hour. That's fast enough to cross the entire United States in just over 10 minutes. Yet astronauts say the experience does not feel like speed. Inside the station, there is no rumbling floor or shaking seat. There is no wind rushing past. There is no sensation of movement at all. They describe it as floating in a quiet room. From their perspective, the station is the still place. They only notice motion when they look out the window and see Earth sliding beneath them in a blur of oceans and continents. Without that visual cue, their bodies feel weightless, calm, and steady because the motion around them is perfectly smooth. Back on Earth, you can see the same effect in one of the most elegant demonstrations ever built, the Foucault pendulum. If you've seen one in a museum, it might have been quietly swinging back and forth above a circular floor, tracing a slow path across a ring of tiles or metal pins. The pendulum doesn't twist or turn by itself, it simply swings. But over the course of hours, the path seems to rotate. Visitors come and go, and the line of motion gradually shifts. It's easy to assume the pendulum is moving, but what you're really seeing is the floor turning underneath it. The Earth is rotating, carrying the room along with it. The pendulum is simply obeying the same rule you feel on a plane. Motion stays the same unless something interrupts it. That's why scientists like to say, the floor is moving, not the pendulum. And the same is true for you. You are like that pendulum, suspended in a turning world. You feel still because everything around you, your frame of reference, your entire environment, moves with you so smoothly that there is no hint of the enormous motion happening beneath your feet. Once you understand this, the calm you feel becomes easier to trust. Your stillness is not a sign that you've been left out of the universe's movement. It is a sign that the universe has placed you inside a stable pocket of motion, where the forces acting on you are perfectly balanced. Nothing pushes suddenly. Nothing throws you off. You are carried gently, continuously, without interruption. You only feel movement when something changes. Acceleration, deceleration, a jolt, a shift. But when everything moves together in harmony, the motion becomes invisible. That is why you can live your entire life on a spinning planet without ever feeling the spin. It's why the oceans don't slosh sideways. It's why trees don't lean backward like flags in a hurricane. It's why the air doesn't tear across the landscape at 1,000 miles an hour. Everything shares the same smooth journey around the axis of Earth. You are a passenger on a flight that never takes off and never lands, moving through space on a path that began long before you were born and will continue long after you are gone. And because nothing in that motion jolts or drags or shifts beneath you, you are free to feel the gentle illusion of rest. In an inertial frame, motion is invisible. Those words explain your everyday life more than you might expect. They explain why you feel grounded when you are actually flying through space. They explain why a quiet room can sit comfortably on a spinning globe. And they explain why your own senses sometimes hide the deeper truth in front of you. The universe does not need your permission to move. It only needs to move smoothly enough that you do not notice. When you sit back and let that idea settle in, something interesting happens. The world feels a little safer, a little calmer, because you recognize that motion does not threaten you. It supports you. It has been supporting you since the moment you took your first breath. And the more you understand that, the easier it becomes to relax into the steady, endless turning of the planet below you. If motion feels like rest, then where did this endless motion begin? If today's motion feels so ordinary, we have to travel back to the one moment when nothing about motion was ordinary at all, the birth of the universe. To understand why everything is spinning now, you have to go back to a time when nothing existed in any familiar sense. No planets, no stars, no galaxies, not even space or time the way you think of them. Just a newborn universe, smaller than a grain of sand, hotter than anything you can imagine, and vibrating with a kind of restless energy that would one day become everything you have ever seen or touched. Tonight, you get to walk backward through that history, all the way to the moment when the first hint of rotation slipped into reality. Imagine winding the cosmic clock back past every human story, every rise and fall of civilizations, past the formation of Earth, past the birth of the sun, past the swirling cloud of gas that gave life to our solar system. Keep going, past the earliest galaxies, past the first stars, past the moment when light itself became free to travel. You keep going until you are standing at the very edge of knowability, the Planck era, a fraction of a second so small that numbers barely cling to it. This is the frontier where the familiar laws of physics bend and blur. Space is not yet smooth. Time is not yet steady. Everything is flickering, trembling, vibrating with quantum uncertainty. And in that chaos, something important is already happening. The universe is filled with fields, invisible structures that exist everywhere, even in total emptiness. These fields are never perfectly still. They shiver with tiny, spontaneous fluctuations, little ripples, little bumps, little oscillations that appear and disappear in unimaginably short moments. Under normal conditions, these tiny tremors would stay tiny forever. But the early universe was not normal. In the first fraction of a second after the Big Bang, something extraordinary happened. Inflation. A burst of expansion so fast, so violent, that it stretched those tiny ripples across the universe like wet paint smeared across an entire wall in a single motion. Imagine placing a fingertip in a calm pond and making the smallest ripple. Then imagine someone instantly enlarging that pond to the size of a galaxy. The ripple would become enormous, but its pattern would stay the same. That is what inflation did. It took the quantum wiggles of the Planck era and amplified them into the seeds of cosmic structure. Those small irregularities became slight differences in density, slight differences in temperature, slight differences in the distribution of energy. And those slight differences were enough. The cosmic microwave background, the faint, ancient light still glowing around you even now, carries the fingerprints of those early ripples. It is almost perfectly uniform. Almost. But if you map its temperature with enough precision, you find tiny variations. Warmer spots, cooler spots, like freckles on the face of the universe. These variations hold clues about the first motions that shaped the cosmos. Some of them even line up in ways that suggest a subtle preference, a gentle asymmetry, a direction that seems slightly favored. Some cosmologists call this alignment the axis of evil, not because it's ominous, but because it challenges assumptions about perfect randomness. It suggests that the earliest universe may have had a faint, whisper-level bias toward a certain direction. Not much, just enough. And that is all motion ever needs. One small imbalance, one slight nudge, one ripple made large. Those quantum tremors were also carried into the structure of space-time itself. As inflation blew the universe outward, the fabric of space absorbed tiny twists, patterns that later showed up as B-modes in primordial gravitational waves. These B-modes are like the swirl marks left behind by water that once spiraled in a bucket. They are the signature of something spinning, stretching, or twisting before anything solid existed to carry momentum. Then, as the universe cooled and slowed, gravity began to gather matter into clumps. Tiny density differences became clouds of gas. Clouds of gas became whirlpools. Whirlpools became galaxies, and galaxies became homes for stars and planets. Each collapsing cloud inherited some of the original asymmetry. Even if the rotation was tiny, nearly undetectable, gravity tightened it. When a cloud shrinks, it spins faster, just like a figure skater twirling with arms pulled in. Billions of such clouds formed stars. Around many of those stars, disks of dust and gas flattened and spun, eventually forming planets, moons, asteroids, and comets. This is why everything you see in the night sky turns. The sun spins, Earth spins, Jupiter spins faster than any planet in our system. Galaxies rotate in vast spirals. Clusters of galaxies rotate slowly around shared centers of mass. Even on scales smaller than the eye can see, rotation is woven into matter. Elementary particles have a kind of built-in angular momentum called spin. Atoms carry rotation-like properties that determine how they bond and interact. Rotation is not an exception in nature. It is the rule. And it all traces back to one simple truth. The universe did not begin perfectly. If the Big Bang had been perfectly smooth, if every part of the universe had expanded with flawless symmetry, nothing would have ever clumped together. No galaxies, no stars, no planets, no life. No you lying here now, listening to the story of how motion began. Perfect symmetry would have given us nothing. It's the flaws that gave us spin. And when you think about that long enough, it becomes strangely comforting. The rotation of galaxies, the formation of worlds, the chemistry of life, all of it emerged from small imperfections. Tonight, as you listen, those imperfections continue to guide the turning of the cosmos, shaping every sunset, every orbit, every spiral of DNA. The cosmos is within us. We are made of star stuff. Those words are more than poetic. They are literal. The elements in your body were forged in ancient stars that once spun in the early galaxies seeded by quantum ripples. Your existence is one long echo of those first vibrations, magnified across billions of years. The universe did not start perfectly still. It started with a preference, a tiny bias for motion. and from that bias came everything. Once the universe learned how to spin, the next question was simple. Could spinning make a place like Earth livable? When you step outside in the early morning, maybe on your way to work, or just to feel the air before the day begins, you probably don't think about the fact that the warm glow on your skin is the direct result of a planet turning beneath your feet. Sunrise is so ordinary, so gentle, that it feels like the world simply decides to light itself for a while. But that soft transition from darkness to morning, and later from afternoon to dusk, only exists because Earth spins at just the right speed. If Earth didn't rotate, there would be no day and night as you know them. One side would face the sun endlessly, locked in a furnace of unbroken heat. The other side would stare into space, collapsing under bitter cold. Any atmosphere that remained would circulate sluggishly, unable to move warmth around the planet. Oceans would freeze and boil depending on which side of the world they sat. Weather systems would die. Temperature gradients would vanish. Life, if it ever began at all, would cling to a narrow twilight strip between light and darkness. But because Earth spins once every 24 hours, sunlight is distributed like a slow, steady breath. Warmth arrives, spreads, softens, fades, and returns. The world takes turns being illuminated and cooled. Plants lean toward the light not because it stays still, but because it moves. Animals migrate, hunt, sleep, and wake according to a rhythm written into the motion of the planet. And you, without noticing, live by the same cycle. Yet the story of Earth's rotation is not just about light. Deep below your feet, far beneath the crust and the mantle of hot, pressurized rock, Earth's core is doing something extraordinary. The outer core is made of molten iron and nickel, swirling around a solid inner core that spins at its own subtle pace. These flowing metals behave like the coils in an enormous generator. As they churn, they create electric currents. Those currents produce a magnetic field. That magnetic field surrounds the planet as a shield, a protective bubble called the magnetosphere. You can't see it. You can't feel it. But without it, the solar wind, a constant stream of charged particles from the sun, would strip away the atmosphere, molecule by molecule. High-energy radiation would bombard the ground. Water would escape into space. The air you breathe would vanish every second, while you sleep, while you work, while you listen to this. The magnetosphere deflects billions of particles that could destroy the fragile balance of life at Earth's surface. And that shield exists because the planet spins. The rotation helps stir the molten core, powering the dynamo that keeps the magnetic field alive. The same rotation that makes sunsets beautiful is also the shield that keeps you alive. On the surface, Earth's spin shapes the world in other ways too. As the planet turns, air moves with it, but not perfectly. Because Earth is a sphere, spinning faster at the equator than at the poles, the moving air is constantly deflected. This effect is called the Coriolis force, and you've seen its influence every time you've looked at a weather map. Storms don't simply blow across the land. They curl. They rotate. They form immense spirals visible from space. Hurricanes spin one direction in the northern hemisphere, and the opposite in the southern. Jet streams twist like ribbons. Ocean currents arc and meander, redistributing heat across thousands of miles. Without these swirling patterns, climates would stagnate, Hot regions would stay scorching. Cold regions would deepen into ice. Instead, because Earth rotates at just the right speed, heat is shuffled around the planet, allowing a remarkable range of temperatures and environments to exist simultaneously. It is this continuous rebalancing that gives the world deserts and forests, monsoons and gentle breezes, storms and calm seas. Rotation even threads its way into your biology. You carry a clock inside your brain, a circadian rhythm that aligns with the 24-hour cycle of light and darkness. Your hormones, metabolism, alertness, and sleep depend on that rhythm. Plants open their leaves according to it. Birds navigate with it. Coral reefs synchronize spawning with it. The planet turns, and life turns with it. Earth's spin is not the only way to build a world, though. Other planets show you what different rotations look like. Jupiter, for instance, spins so fast that its day is only about 10 hours long. The rapid rotation tears its atmosphere into violent bands. Storms the size of continents churn for centuries. The Great Red Spot is a hurricane so massive that Earth could fit inside it. Venus, on the other hand, rotates painfully slowly and in the opposite direction of most planets. A single day there lasts longer than a Venusian year. Its atmosphere crashes down with temperatures hot enough to melt lead. Without a strong rotation, its magnetic field is weak. Solar wind strips at it relentlessly. The clouds trap heat with brutal efficiency. No sunrise or sunset breaks the monotony. Mars offers a different lesson. Its day is similar to Earth's, about 24.5 hours. And once, long ago, it likely had rivers, lakes, and maybe even an ocean. But its smaller size allowed its core to cool. Without a molten dynamo, its magnetic field faded. Solar wind eroded its atmosphere. The surface became dry, cold, and exposed. Rotation alone wasn't enough. It needed the shield that rotation once helped create. These worlds remind you of something profound. Earth's rotation is not too fast, not too slow, not too tilted, not too chaotic. It is balanced in a narrow band where sunlight can cycle gently, weather can circulate, oceans can breathe, and the planet can protect life with an invisible shield. You live on a rotating miracle, thin-skinned and shielded by invisible magnetism. If Earth's rotation slowed by even half, the difference would be dramatic. Days would stretch toward 50 hours. Nights would grow equally long. Heat would build mercilessly on the sunlit side, and cold would deepen on the dark side. Weather systems would intensify. Storms would grow broader and more violent. The rhythm of sleep and wakefulness would drift out of sync. Every living thing would have to adapt or fail. If Earth rotated faster, the equator would bulge outward. Winds would intensify. Storms would form more quickly and spin more fiercely. The atmosphere would redistribute heat with dizzying speed. Humans would feel heavier due to increased centrifugal force near the equator. Even the length of the day would shrink. But Earth rotates at a pace that threads the needle, fast enough to distribute light and heat, slow enough to stay calm and livable. Its spin is not background noise. It is a life support system. Tonight, as you lie here, breathing evenly, the magnetosphere is quietly blocking radiation from the sun. Oceans are circulating warmth around the world. Winds are curving gently, redistributing air. Sunlight is moving towards someone else on the far side of the globe. All because the planet beneath you keeps turning. And now that you understand how rotation protects and nourishes life. It's time to explore something stranger. When rotation becomes extreme, it doesn't just shape weather or sunsets. It begins to bend something far deeper, time itself. As you lie here, in the quiet of your room, the world around you feels steady. Time feels steady too. A second is a second. A minute is a minute. You can almost hear the rhythm of your own life moving forward at its usual pace. But out in the universe, especially in the most extreme places, that rhythm can stretch, slow, twist, or even tear, depending on how fast something is spinning. That idea feels almost mythical at first, like a story whispered around a campfire. But it's real, and it's one of the most beautiful, mind-bending truths in physics. To understand it, you have to start with a quiet reminder from general relativity. Mass and energy bend the fabric of space and time. Not metaphorically, literally. Space curves. Time dilates. Gravity isn't just a force pulling you downward. It's the shape of the universe telling objects how to move. Most of the time, this curvature is gentle. Earth's gravity slows time by an amount so tiny that you would never notice it in your daily life. But when something spins, truly spins, gravity begins doing something stranger. It doesn't just curve space-time, it drags it. Imagine lowering a spinning ball into a giant vat of honey. The honey closest to the surface of the ball begins swirling. Layers farther out swirl a little less. The rotation spreads outward, pulling the fluid around it. This is what happens near any massive spinning object, except the honey is the fabric of space-time itself. Scientists call this phenomenon frame dragging, and it's not theoretical. It has been measured. Gravity Probe B, one of the most delicate satellite experiments ever made, detected space-time being gently twisted around Earth as our planet rotated. The effect is small here, almost tender. But around extreme objects, the twisting becomes violent, reshaping time itself. Take neutron stars. They are what remains after massive stars explode and collapse. Imagine cramming the mass of the sun into an object only as wide as a city. The density is unimaginable. A teaspoon of neutron star material would weigh more than a mountain. Many neutron stars rotate dozens of times per second. Some whirl hundreds of times a second. If you stood near the surface of a rapidly spinning neutron star, though nothing human could survive there, you would experience time differently. Your seconds would stretch. Your minutes would slow. If someone watched you from far away, your movements would appear sluggish, as if the universe had turned up the thickness of time around you. The difference could be tiny or enormous, depending on how extreme the spin is. And then there are pulsars, neutron stars that sweep beams of radiation across space like cosmic lighthouses. As they rotate, each beam blinks past Earth at astonishing regularity. Some pulsars are more stable than atomic clocks. Their spins are so precise that entire fields of astrophysics use them to measure the universe. In a strange way, these dead stars become the timekeepers of the cosmos. Their perfect timing is a direct result of unimaginable spin. But even neutron stars are gentle compared to what comes next. In the realm of black holes, specifically spinning black holes called Kerr black holes, space-time is pushed to its limits. These objects don't just drag the fabric of space. They whip it. They twist it. They force it into a chaotic whirlpool where nothing behaves the way you expect. Around a Kerr black hole, is a region called the ergosphere. It is not part of the event horizon yet, but it is already too twisted for anything to remain still. Inside the ergosphere, even if you tried to hover with rockets pointed outward, you would still be dragged into rotation. Space-time itself is swirling so powerfully that all paths curve. Everything must spin with the black hole. Light, matter, even time. The images captured by the Event Horizon Telescope, those donut-shaped glows around M87 and Sagittarius A, hint at this violence. The light itself is sculpted by the spin, sharpened, flattened, distorted. You are seeing not just matter falling inward, but space-time being pushed and stretched by rotation. Time doesn't flow the same way near these objects. It doesn't flow at the same rate. It doesn't even keep the same rules. Somewhere out there, a star is spinning so fast that if you watched from its surface, your entire life would pass at a different pace. This isn't just science fiction. We use this knowledge every day. If you use GPS, on your phone, in your car, anywhere, you rely on satellites whose clocks tick differently from clocks on Earth because they orbit higher, where gravity is weaker and frame dragging is softer. Time moves slightly faster for them. Their clocks must be corrected so your location stays accurate. If engineers didn't account for this difference, if they ignored the warping of time caused by gravity and motion, your GPS would drift by miles each day. Navigation would fail. Mapping would collapse. Something as ordinary as finding an address would become impossible. The clocks we trust are quietly negotiating with gravity and spin every second. Now imagine taking that negotiation and turning it up to cosmic levels. Spinning stars, crushed remnants of supernovae, and black holes that drag entire regions of the universe into co-rotation. In those places, time becomes a local thing, a variable shaped by environment, not a constant shared by all observers. Time is not a universal river. In the presence of spin and gravity, it becomes a series of local whirlpools. The more extreme the whirlpool, the more time slows. The more intense the drag, the more space warps. What you think of as the simple passing of seconds becomes a fragile and shifting phenomenon. In a very real way, time depends on where you are, how fast you're moving, and what you're moving around. Lying in your room, this may feel distant, like watching a myth play out across galaxies. But the truth touches your life more than you realize. Without these distortions, without the flexibility of time, many of the systems you depend on each day would crumble. And without the lessons from extreme spinning objects, we would never understand the deeper structure of the universe. Time is what keeps everything from happening at once. And yet, out there in the darkest corners of the cosmos, rotation is rewriting time's rules, sculpting the rhythm of existence in ways that defy intuition. It bends time without breaking it, stretches seconds without tearing them apart, and shows you that the universe is far more fluid, far more elastic than the ticking of a clock might suggest. If spin can bend time, then we have to ask a more personal question. Who controls the spins that define your time? Take a breath. Let the room settle around you. Because now, we're stepping into something surprisingly intimate. The way the universe keeps time. Not time as a number on your phone, not time as a schedule or a deadline, but time as a physical phenomenon, one that only exists because matter is spinning at every scale. It sounds abstract, but the truth is wonderfully simple. Every second you've lived is a handshake between atomic spins and a spinning planet. To see how deep that handshake goes, start with the most ordinary question imaginable. What is a second? It feels like a basic unit, a tiny piece of the day you chop into manageable moments. But the second is not defined by a clock on a wall or by the turning of the earth. Not anymore. Modern time is anchored to something far smaller and far more fundamental. Your clock, and every clock synchronized with global standards, ultimately depends on the behavior of electrons inside atoms, specifically inside the element cesium. When electrons change energy levels, they release or absorb radiation at an exquisitely consistent frequency. That frequency is tied to a quantum property called spin, a kind of built-in angular momentum that defines how electrons behave. Scientists counted those oscillations, 992,631,170 of them, and declared that when cesium completes that many cycles, exactly 1 second has passed. In other words, the world measures time by watching electrons, tiny spinning clouds of probability, flip between two states like microscopic gears. The second isn't floating in some metaphysical space. It rises from motion at the smallest scale we know. And yet, for most of human history, we didn't measure seconds that way. We looked up. A day was the time Earth took to spin once on its axis. A year was the time Earth took to orbit the sun. Every calendar, every season, every ancient ritual, every harvest, every navigational chart, everything tied its rhythm to the turning of the planet. You woke with the light and slept with the darkness because Earth spun beneath you. You celebrated the return of spring because Earth completed one more loop around the sun. Time was not an idea. It was a rotation. It was motion turned into meaning. But Earth doesn't spin perfectly. The tides, pulled by the moon, act like a brake. Over millions of years, Earth's rotation has been slowing, just a little, but enough that clocks notice. Some years, we have to add a leap second to keep atomic time aligned with Earth time. Engineers freeze the world's digital clocks for one extra heartbeat to pull the two systems back into sync. That quiet adjustment happens because the planet beneath you is gradually losing rotational energy, bit by bit, as tidal forces stretch and flex the oceans. It's humbling to realize that even the steady ticking of time depends on the dance between Earth and Moon. Your daily schedule is, in its own way, a consequence of celestial mechanics. But the deeper question is this: if everything is spinning, who or what keeps it spinning? Who winds the cosmic gears? Why doesn't Earth slow to a stop tomorrow? Why doesn't the galaxy grind to a halt? The answer is one of the most elegant ideas in physics: the conservation of angular momentum. Momentum is stubborn. Once something starts moving, it resists stopping unless a force pushes back. And in the vacuum of space, where friction is almost non-existent, there's nothing to push back. That's why a cloud of gas collapsing under gravity speeds up as it shrinks, the same way a figure skater spins faster when they pull their arms in. The motion doesn't come from nowhere. It concentrates. It preserves itself. It's the same invisible principle that lets Earth keep turning after billions of years. The same principle that keeps the sun spinning. The same principle that keeps galaxies rotating in vast spirals. Nothing external needs to push them along. They continue because the universe doesn't forget its own motion. In that sense, your timeline, your birthdays, your work weeks, your quiet nights like this one, are all tied to angular momentum that has been conserved since the dawn of the cosmos. Time is not written on the sky. It's carved into motion. Think about the clocks you carry or wear. The smooth second hand sweeping across a dial. The digital numbers glowing softly on your nightstand. The notifications arriving at predictable moments. All of that depends on motions so consistent, so reliable, that they can be used as a foundation for society itself. Your wristwatch measures the beat of a tiny oscillator. Your phone measures vibrations in a quartz crystal. Your computer syncs to a time standard anchored in cesium atoms. And all of those things succeed because nature gives us a universe where spin, once created, stays stable enough to serve as a clock. We are prisoners of time, yet we built the prison ourselves out of spinning things. When you use a calendar, you're trusting the orbit of Earth. When you watch a sunset, you're trusting Earth's axial rotation. When you look up at the moon, you're seeing a world kept in orbit by momentum so ancient that it predates life itself. Even on the scale of galaxies, time is anchored to motion. Spiral galaxies spin so persistently that their rotation curves helped reveal dark matter, an invisible mass that keeps them from flying apart. Their years, their epochs, their evolution all depend on the conservation of spin inherited from the Big Bang. So the next time you think of time as something arbitrary, a number people invented, a human-made system, remember this. Your seconds come from electrons. Your days come from Earth's rotation. Your years come from Earth's orbit. Your seasons come from axial tilt. Your tides come from the moon tugging gently at Earth's spin. Every appointment, every memory, every birthday celebration has been living inside a framework set by cosmic motion, from quantum scales to planetary ones. The tick of your life is not independent of the universe. It is synchronized with it. And what's even more beautiful is this. Time, as you know it, requires the universe to be imperfect. If everything had been perfectly symmetrical after the Big Bang, no ripples, no variations, no unevenness, nothing would have spun. Nothing would have collapsed into stars. Nothing would have orbited anything else. A perfectly balanced universe would be sterile. To get structure, you need something more unsettling, broken symmetry. And that is where we go next. Because the same small deviations that created spin also created complexity, diversity, and the cosmic landscapes you know today. But a perfectly spinning, perfectly balanced universe would be sterile. To get structure, you need something more unsettling, broken symmetry. If you want to understand why anything in the universe spins, why planets rotate, why galaxies swirl, why atoms have built-in angular momentum, you have to begin with a strange, almost uncomfortable truth. Nothing interesting can happen in a perfectly symmetrical universe. Picture a cosmos that is flawlessly even. No warm spots, no cool spots, no fluctuations, no bumps or wiggles or density differences. Everything exactly the same everywhere. At first, that sounds peaceful, orderly, elegant, pure. But look closer. In that universe, nothing would have a reason to turn. Nothing would clump together. Nothing would flow, or collapse, or orbit. Perfect symmetry means perfect stillness. If every point is the same as every other point, then no direction is special. No axis is preferred, no up or down, no left or right, nothing to begin a twist. In such a universe, motion would have no story to tell. But the universe you live in isn't like that. And the reason is that symmetry did break. Not violently, but subtly, quietly, decisively. And that tiny break, that small departure from perfection, is why you exist. After the Big Bang, the universe was unimaginably hot and dense, and all the forces of nature, gravity, electromagnetism, the strong force, the weak force, were united as a single, symmetrical interaction. As the universe expanded and cooled, that symmetry fractured. The forces split apart, each one taking on its own personality. Gravity pulled in. Electromagnetism pushed and attracted. The strong force glued quarks into protons and neutrons. The weak force let particles decay. This moment, called spontaneous symmetry breaking, wasn't dramatic in the way explosions are dramatic. It was more like a perfectly balanced table that suddenly tilts by a millimeter. Just enough for a marble to start rolling. Just enough to create direction where none existed. The cosmic microwave background, the fossil light left behind from when the universe was only 380,000 years old, carries the fingerprints of that tilt. It is almost uniform, but not quite. Some regions are a tiny fraction of a degree warmer, others slightly cooler. These temperature ripples are incredibly small, differences of less than 1 part in 100,000 hours. But they were enough to grow into galaxies, clusters, stars, planets, oceans, and you. Symmetry is beautiful, but broken symmetry is interesting. Those tiny temperature differences are the reason matter had places to fall into. They are the first hints that the universe was not perfect and did not want to be. But the greatest asymmetry of all was far more dramatic. It involved matter and antimatter. In the first fraction of a second after the Big Bang, the universe created particles of matter and particles of antimatter in nearly equal numbers. When matter and antimatter meet, they annihilate in a flash of pure energy. Logic says the universe should have ended in a clean, beautiful blaze, leaving behind nothing but light. No atoms, no planets, no life. But that isn't what happened. Some tiny preference in the laws of physics, favored matter just a little. For every billion antimatter particles created, there were 1,000,000,001 matter particles. That difference, 1 part in 1,000,000,000, is why anything exists today. Everything you see around you, everything you have ever known, is built out of the leftovers from that tiny unfairness. That small tilt in nature's balance sheet is called CP violation. It means the universe is not completely impartial. It leans just slightly in one direction. Your entire life depends on a tiny violation of perfect fairness at the dawn of time. This imbalance allowed matter to survive long enough to form atoms. But atoms themselves needed another broken symmetry to gain mass. That's where the Higgs field enters the story. As the universe cooled further, the Higgs field settled into a value that was no longer symmetrical. Particles passing through it suddenly behaved as if they had mass. They slowed down. They clumped together. They began forming structure. Once particles had mass, gravity could gather them. Once gravity gathered them, clouds formed. Once clouds formed, rotation emerged. Even the direction of time, what we call the arrow of time, comes from asymmetry. If the universe had started perfectly symmetrical, there would be no difference between past and future. no evolution, no growth, no directionality. Instead, entropy increased, structure formed, and rotation became a natural way for energy and matter to distribute themselves. Spin, in a sense, is frozen asymmetry. It's what happens when the universe tries to express a preference. Think of a perfectly level ping pong table. Put a ball on it, and the ball won't roll. There's no slope, no bias. Now tilt the table by a fraction of a degree. The ball begins to move. Not because you pushed it, but because the symmetry was broken. The universe works the same way. It tilts, it chooses, and motion follows. The earliest tiny ripples grew into swirling galaxies. The earliest imperfections created stars that rotate. The earliest asymmetries gave planets their spins. If the universe had been perfectly symmetrical, you would not be here to wonder about any of this. You wouldn't be lying in your room, listening to a story about motion. You wouldn't have atoms, or chemistry, or DNA, or breath. You'd have nothing at all, because a symmetrical universe has no reason to do anything except remain empty and still. In physics, unfairness is not a bug. It's the feature that lets universes spin up structure. Those little violations of balance didn't just produce clumps of matter. They produced momentum. They produced direction. They produced rotation at every level, from electrons to galaxies. They gave the universe texture, character, and the ability to evolve. The universe chose a side. That tiny choice gave us everything that spins today. Now picture everything you've learned so far. Quantum ripples stretched by inflation, gravitational collapse speeding up rotation, conserved momentum carrying motion forward for billions of years. All of it built on slight imperfections, fault lines and symmetry. This is the heartbeat behind all cosmic motion. The reason the universe has structure, complexity, and time that flows from past to future. Once the universe had mass, structure, and a taste for imperfection, it built something huge and wildly unstable, spinning galaxies. If you could step outside the Milky Way and look at it from far away, from a vantage point where the entire galaxy fits neatly into view, you would see something astonishing. A luminous disk of hundreds of billions of stars, arranged in spiraling arms, all rotating gracefully around a glowing center. The whole structure looks delicate, like a cosmic pinwheel, turning slowly in the dark. But slowly is an illusion. The stars in our galaxy are racing. The sun itself is moving at about 500,000 miles per hour around the galactic center. The Milky Way, like other spiral galaxies, is a giant disk spinning so fast that by all ordinary physics, it should tear itself apart. Yet it doesn't. Something unseen is holding it together. The first hints of this mystery appeared in the 1930s, when astronomer Fritz Zwicky studied clusters of galaxies, huge collections of hundreds or thousands of galaxies bound together by gravity. He discovered that the galaxies inside these clusters moved far too quickly to be held in place by the mass that telescopes could observe. If the only mass in the clusters came from stars and gas, the clusters should fling themselves open and drift apart like sparks from a firework. But they didn't. Zwicky proposed something radical. There must be invisible mass, dunkle materie, or dark matter, keeping the clusters from flying apart. Most scientists didn't take the idea seriously at the time. It was bold. It was strange. It seemed more like speculation than science. It would take another 40 years for the mystery to deepen, thanks to a quiet, meticulous astronomer named Vera Rubin. She studied how stars move in spiral galaxies. The expectation, based on Newton's laws, was clear. Stars near the center of a galaxy should orbit quickly, while stars farther out should orbit more slowly. Just like planets far from the sun move more slowly than planets that are close in. But that wasn't what Rubin found, not even close. Instead of decreasing, the orbital speeds of stars far from the center stayed almost constant. They formed a flat line, a rotation curve that made no sense if all the mass in the galaxy came from stars and gas. Imagine spinning a merry-go-round. Objects near the middle can safely go fast. But objects at the edge, if they go too fast, should fly off. A galaxy works the same way. There has to be enough mass holding the outer stars in place. But Rubin's data showed there wasn't nearly enough visible mass to account for the speeds she measured. Something invisible was anchoring those outer stars. Something massive and widespread. Something forming a spherical halo around each galaxy, outweighing the luminous parts by a factor of 5 or more. Rubin's work changed our view of the universe forever. It wasn't just galaxy clusters that needed dark matter. It was individual galaxies themselves. Every spiral galaxy you've ever seen, a bright whirl of starlight, is really spinning inside a vast invisible cocoon of dark matter. What you can't see is what keeps everything together when it spins too fast. The evidence kept growing. One of the most dramatic pieces appeared in the Bullet Cluster, 2 galaxy clusters that collided like 2 slow-motion clouds of stars. When astronomers mapped where the visible matter went, mainly hot gas, it lagged behind the collision, slowed by friction. But when they mapped the gravitational mass using gravitational lensing, the mass wasn't where the gas was. It had moved through the collision almost unaffected. The mass was somewhere else, leading the gas, not following it. That mass couldn't be made of normal matter. It was something invisible. We can't see dark matter. We can't touch it. We can't make it in a lab. But we can see its fingerprints in the way galaxies spin. Today, the picture looks like this. About 5% of the universe is made of ordinary matter, the stuff you're familiar with: stars, planets, air, oceans, you. About 27% is dark matter, the invisible scaffolding that gives galaxies their shape and stability. The remaining 68% is dark energy, an even stranger component driving the expansion of the universe. You live in the 5%, held in orbit by the 95% you'll never see. And that's not frightening. It's strangely comforting. Because even though dark matter is invisible, it behaves predictably. It creates gravitational wells that cradle galaxies, holding them together like a skeleton holds a body together. Without it, galaxies would wind apart. Stars would drift into the void. Planetary systems would unravel. The universe doesn't just spin. It spins on scaffolding made of mystery. Think again of that image of the Milky Way, the glowing spiral turning in the dark. Beneath the visible stars is a vast, transparent halo of mass extending far beyond the luminous arms, shaping the rotation of everything inside it. That halo is what keeps the galaxy from tearing itself open under its own speed. Dark matter is the steady hand on the unseen wheel, the quiet stabilizer, the invisible balance that lets galaxies whirl for billions of years. As you lie here tonight, listening. The entire Milky Way is sweeping through space in a gentle arc, its stars circling the center, its spiral arms rotating slowly, all of it supported by a halo of matter that has never once glowed. It's a cosmic reminder that not everything real has to be visible, and not everything important has to shine. We are still groping for the nature of dark matter, but we can see its fingerprints in the way galaxies spin. Once you accept that invisible matter can decide how galaxies spin, another question rises quietly, almost naturally. If invisible matter can decide how galaxies spin, could invisible rules also decide how life itself twists and coils? As you listen tonight, you're lying on a planet held together by rotation, inside a galaxy shaped by rotation, inside a universe whose earliest ripples created motion at every scale. But now, the story becomes more personal. Because the universe didn't stop twisting when it built galaxies, it carried that twist inward, into matter, into chemistry, into the architecture of life itself. Every cell in your body remembers a cosmic decision about left and right. To understand that, start with a simple idea: chirality. Hold your hands up in the dark. Your left and right hands look similar, but you can't place one on top of the other and make them match. They are mirror images, similar but not identical. Molecules can be like that too. Some have a left-handed version and a right-handed version. Same atoms, same arrangement, but twisted in opposite directions. And here's the strange part. Life on Earth uses almost exclusively the left-handed versions of amino acids. Nearly every protein in your body, every enzyme that keeps you alive, is built from left-handed building blocks. If you swap them for right-handed ones, the molecules would still exist, but they wouldn't work. Your cells wouldn't recognize them. Life, as you know it, would collapse. DNA carries a twist too. A spiral staircase coiled in a specific direction. RNA coils in the same handedness. If their twist were reversed, the entire machinery of biology would fail. Enzymes wouldn't bind correctly. Replication wouldn't proceed. The elegant zipper-like mechanism that copies your genetic code would jam. The spiral of your DNA is not random. It carries the signature of the spinning universe that built it. But why left-handed? Why not right? Why should life care? To this day, no one fully knows. But the clues point back to the cosmos. When stars are young, they fire jets of ultraviolet light. Some of this light is polarized. It vibrates in a single orientation. Polarized light interacts with left and right-handed molecules differently. In laboratory experiments, polarized ultraviolet radiation preferentially destroys one-handedness more than the other, leaving behind an excess of the survivor. Now imagine a cloud of gas and dust around a newborn star, the kind of cloud that might someday collapse into planets. If polarized starlight washes through that cloud, destroying just a little more of one version of a molecule, the surviving version may begin to dominate. That dominance gets amplified as molecules combine, react, and gradually form the organic compounds that seed life. Evidence for this idea has shown up in surprising places. In 1969, a meteorite called the Murchison meteorite fell in Australia. Inside it, scientists found amino acids with a left-handed bias, similar to the bias found in Earth life. Those molecules had been drifting in space long before Earth formed, carrying a preference written somewhere in the chemistry of the early solar system. Later, the Rosetta spacecraft visited a comet named 67P. Instruments detected complex organic molecules there too, again showing asymmetries that hint at cosmic origins for life's handedness. Even fundamental particles display bias. Neutrinos, for example, are always left-handed. They spin in a way that aligns with motion in only one sense. Their mirror image counterparts, right-handed neutrinos, have never been observed in nature. The universe itself seems to have a preference, a tilt, a lean, a subtle choice that echoes through chemistry and biology. All of this suggests something profound. Life didn't just appear on a spinning planet. Life itself is a pattern of spin. When you think about your body, you may imagine it as a static structure, a shape of flesh and bone. But at a microscopic level, your body is a choreography of twisted molecules. Every strand of DNA, every protein, every enzyme is arranged with a handedness that can be traced back to polarized starlight, to cosmic asymmetry, to ancient magnetic fields, perhaps even to the rotation of the galaxy itself. Picture the Milky Way turning through space, dragging magnetic fields and polarized radiation with it. Picture clouds of dust drifting in those fields. Picture molecules tumbling through those clouds, some broken apart by polarized light, others surviving. Eventually, those surviving molecules gather, combine, and form precursors to biology. They carry a preference, a twist, a memory of the conditions that shaped them. Billions of years later, that bias still lives in you, in your cells, in your blood, in the double helix unfurling and folding inside you every second. What if DNA had twisted the other way? What if amino acids had been right-handed instead of left? What if polarized starlight had struck a slightly different angle, or the galaxy's magnetic field had been oriented differently, or the early solar system had formed in another pocket of the universe? Life might still have existed, but it wouldn't be this life. It wouldn't be familiar. And it might not have been able to evolve into beings capable of asking these questions. You are, in a very real sense, the universe's way of twisting chemistry into awareness. Everything you are, every thought, every breath, every memory, is built from molecules that inherited their handedness from cosmic forces older than Earth itself. The same asymmetry that allowed galaxies to form also allowed proteins to fold. The same cosmic tilt that shaped the rotation of stars also shaped the double helix of your DNA. There's something soothing in that continuity. The twist in your biology isn't separate from the twist in the cosmos. It's connected. It's part of the same long story of motion that began when the universe was still glowing with its first light. But spins don't last forever. Even the grandest rotations are slowly bleeding their energy into the dark. Right now, as you listen, the universe feels full of motion, full of light, full of turning worlds and spiraling galaxies. But nothing that spins can keep spinning forever. Motion fades, energy spreads, structures unravel. And if you follow the story of spin far enough into the future, you reach a landscape that feels almost like the universe preparing to fall asleep. Don't worry. This is not a frightening journey. It's slow, quiet, and strangely peaceful, like listening to the last few notes of a long cosmic song. Start close to home. The earth beneath you is still rotating, carrying you through day and night. But that rotation is not fixed. The moon, tugging constantly at Earth's oceans, steals a tiny bit of rotational energy with every tide. As the tides pull gently on the moon, they act like brakes on Earth's spin. Very slowly, far too slowly for you to feel. Earth's rotation is decelerating. Days are growing longer by about 2 milliseconds per century. Not much, just a whisper. But over millions of years, those whispers add up. 100 million years from now, a day on Earth may be an hour or more longer than it is now. 1 billion years from now, the difference could be dramatic. Meanwhile, the moon is drifting away from us, about 1.5 inches each year. It once hung much closer in the sky, larger, brighter, exerting stronger tides. In the future, it will appear smaller, dimmer, and more distant. The Earth-Moon dance continues, but the steps grow wider, slower, gentler. Farther ahead still, entire galaxies will shift their patterns of rotation. The Milky Way is not drifting through space alone. On the horizon of cosmic time, another enormous spiral galaxy is approaching us, Andromeda. Right now, Andromeda is moving toward the Milky Way at over 200,000 miles per hour. It looks serene in the night sky, but it is on a collision course with us. 4 billion years from now, the two galaxies will begin to merge. At first, their stars will interpenetrate like ghostly clouds, passing mostly unharmed because the distances between stars are enormous. But their gravitational fields will pull and twist each other. Stars will be flung into new orbits. Entire systems will be rearranged. The spins of both galaxies will be redistributed like two whirlpools merging into one. The spiral arms of each galaxy won't survive the encounter intact. Over time, the combined galaxy, sometimes called Milkdromeda, will likely settle into a more rounded, slower spinning ellipsoidal shape. The elegant spiral structure the Milky Way wears today will fade, replaced by a smoother, more diffuse glow. Spin remains, but it softens. It spreads out. It becomes less defined, less dramatic, less structured. As you move forward even farther, the stars themselves begin to disappear. Stars live long lives, but not infinite ones. The bright, massive stars die quickly, collapsing into neutron stars or black holes. Smaller stars fade more slowly, cooling into white dwarfs, hot, dense embers glowing faintly in the darkness. In the far distant future, white dwarfs will cool until they no longer emit light. The universe will fill with dark remnants, cold white dwarfs, solitary neutron stars, and spinning black holes. Even black holes will lose energy over trillions upon trillions of years. Through processes predicted by quantum mechanics, they slowly leak radiation. It's a tiny effect, almost unimaginably small, but over vast timescales, even the greatest spinning behemoths in the universe will surrender their energy to the dark. Spin fades, slowly, inevitably, at timescales even more immense, timescales so vast that they dwarf the age of the universe. Other transformations may occur. Some theories suggest protons themselves, the building blocks of atoms, may eventually decay. If that turns out to be true, matter will gradually dissolve into simpler and simpler particles. The universe will continue expanding. Galaxies will slide beyond each other's horizons. Energy will spread thinner and thinner. Motion will smooth out. Eventually, you reach the far future known as heat death. Not a violent end, not a collapse, but a quiet erasure of gradients. No temperature differences, no pressure differences, no structures, no cycles, no reasons for anything to spin, flow, or orbit. Imagine a pond so perfectly still that no ripple can ever form again. That is the universe at the end of time. But even here, the spin doesn't disappear in a single moment. It simply becomes irrelevant. It dilutes. It loses definition. It fades into uniformity. The universe doesn't stop spinning so much as it loses the conditions that make spinning meaningful. The universe will not end with a bang, but with a whisper of fading motion. All of this may sound somber, but there is something deeply soothing in the idea, because it means you are alive at a very special moment, not too early, not too late, in a universe that is still full of structure, full of contrast, full of the gradients and imperfections that make motion possible. Every rotation you've ever known is temporary, and that temporariness is what makes it precious. The sun still burns, Earth still turns, galaxies still spiral, stars are still born from clouds that collapse and spin. Life is still possible. Consciousness still unfolds. You exist in a chapter where motion is rich, where the universe has not yet exhausted its ability to form stars, planets, oceans, and questions. And here, in this quiet room tonight, you get to listen to that story while the world continues its ancient rotation beneath you. The far future will come, but not for an unthinkably long time. Right now, you are living in the bright, vibrant middle of cosmic time, the era of motion, structure, and spin. And that's where you come in, because right now, in this quiet room, the universe is doing something new with its motion. You've traveled a long way tonight, farther than any spacecraft, farther than light itself can carry you in a single lifetime. And now, as everything slows down, your journey folds gently back into the quiet place where it began. Here, in your room, with your own breath, rising and falling as steadily as a planet turning under a star. Think of the path we traced. From the spin of electrons, tiny quantum whirlpools humming at the smallest scales, to the rotation of Earth, the slow, ancient turning that brings you sunrise and darkness, to the swirling of galaxies, vast rivers of stars spiraling around invisible structures. All of it is one continuous story of motion. And tonight, that story has carried you from the beginning of time to the edge of the universe and back. Momentum never truly disappears. It gets passed along, shared, stretched across space and scale. The spin of a collapsing cloud becomes the spin of a star. The spin of a star becomes the spin of planets forming around it. The spin of planets becomes the rhythm of days and nights, the rise and fall of winds, the timing of life. And in a softer way, that same lineage of motion lives in you, in every cell, in every thought. Inside your brain, ions drift, molecules vibrate, electrical impulses ripple from neuron to neuron, small motions, microscopic motions, layered on top of trillion-year-old motions, written into the fabric of matter. When you wonder about the universe wonders about itself through you. You are not outside the story of motion. You are an active frame of it, a conscious swirl in an ocean that has been turning since the first second of creation. Look around your quiet room for a moment. Maybe the city outside has fallen silent. Maybe the house has dimmed to soft shadows. Maybe even your own breathing has relaxed into an easy, effortless rhythm. Nothing seems to be moving, but above you, Earth is spinning steadily, carrying continents, oceans, clouds, and everyone you've ever known in its gentle rotation. And far above that, the Milky Way is turning too, so slowly you could never see it, but so surely that its motion guides the orbits of hundreds of billions of stars. You live cradled inside layers of motion, so smooth, so ancient, so constant, that your senses have learned to call them stillness. And that's all right. Stillness is a gift, one that motion gives you when it becomes perfectly balanced. Tonight, none of this is something you have to solve. Not dark matter, not CP violation, not the fate of galaxies, or the heat death of the cosmos. None of it is waiting for you to fix or figure out. You've already done enough today. You've learned enough tonight. Your curiosity has carried you farther than most people ever travel in their thoughts. Now, let the journey slow. Let the questions soften. Let yourself rest inside the knowledge that you don't need all the answers. You never did. The universe is vast and full of mysteries, but you don't have to hold them all. Not now. Not in this moment. You can set them down, gently, like placing a book on a bedside table. Because here is the quiet truth. You are the way the universe remembers it ever moved at all. Your heartbeat, steady and patient. Your breath, rising and falling. Your thoughts, flickering softly like signals sent across a vast, dark ocean. In every heartbeat, every breath, there's a faint echo of the first motion that started all of this. A whisper of the spin that shaped stars, planets, galaxies, and the molecules that built your body. And in this whisper, you are not small. You are connected. You are held. We are a way for the cosmos to know itself. Those words are gentle because they are true. You are not separate from the universe you've been listening to tonight. You are an expression of its motion, its asymmetry, its persistence, its curiosity. You thought you were just listening to a story about spinning things. All along, you were the main character. As long as you are here, the story of motion is still being told. Through your life, through your memories, through the way you look up at the sky and feel something stir. But it's late now. The world is dim. Your breath is slow. Your mind is settling like dust, drifting down through a quiet beam of light. Tonight, let the universe keep spinning without you for a while. Close your eyes, drift off, and let motion take care of itself.